Hello, everybody. This is Dr. Viv again. In this video, we shall solve explicitly motion with quadratic air resistance in the presence of gravity. And for simplicity, all the motion shall be in the vertical direction. I have indicated here schematically what's going on. Suppose you're throwing a ball vertically up into the air with an initial speed of v0. It's going to get slowed down due to two reasons this time. One is the usual, gravity, and the other is the air resistance that's constantly acting opposite the direction of velocity. Then it reaches the highest point, and that height we shall call by the letter capital H. And at the highest point, it's momentarily not moving, and then it starts coming down. On the way down, air resistance acts up. Because of this, we have to deal with the motion up and the motion down separately, because the equations will be different. On the way up, air resistance and gravity act down. On the way down, when the ball is on the way down, the gravity acts down, but air resistance acts up. So the time taken to go up is called T1. The time taken to go down is called T2. The speed with which you threw the ball is called V0. The speed at the time you catch it is called VF. What you're supposed to show is that when the ball returns to your hand, it has less speed than when you throw it first. And the next part is that show that the time taken to descend is greater than the time taken to ascend. So in terms of the symbols that I have defined here, what we need to show here is that VF is less than V0. And what needs to be shown here is that T2 is bigger than T1. Both of these make sense to you intuitively. This makes sense because energy is constantly being drained from the system through air resistance, and so you can expect the kinetic energy not to be the same. It's in fact less. The time is a slightly more subtle thing to see, but you can make some arguments and convince yourself that the time must be greater. What I should be doing now is actually showing you these things using equations and mathematics. So let's proceed. Let's talk about the phase of going up, or the ascent. Quadratic air resistance means that the object is acted on by the square of the velocity. So the equation of motion is going to be mass times acceleration is equal to negative mg negative b times y dot squared. Here I'm using Newton's notation, whereby dots refer to the time derivatives. So y dot is dy by dt, and y double dot is the y velocity by dt, or in other words, the acceleration. Now, in an earlier video, I showed you if I divide both sides by m, I get negative g, negative b over m, y dot squared, and this b over m can be written as a reciprocal wavelength. Let me repeat that argument here. So the units of b over m come from examining this term and that term. So the units of my double dot must be the same as the units of by dot squared. So the units of b over m must be the same as the units of y double dot over y dot squared. Y double dot is acceleration, and y dot squared is speed squared. So you see that you're left with 1 over meters, which is precisely the units of something with reciprocal wavelength. This lambda, I shall simply call the wavelength, or to be less breezy about it, it is sometimes called the characteristic length. There is really no wave in this problem, so maybe the words characteristic length are more precise. Now, there is something else I would like to define, and that is the notion of the terminal speed. Now, by the way, even though I'm defining this notion of terminal speed, I'm nowhere assuming that terminal speed is reached. So don't be worried. This problem is completely general. I'm just defining this quantity. Terminal speed is said to be achieved when y double dot is 0. So when you set y double dot equal to 0, what I get is terminal speed. Now you can see that terminal speed is best achieved on the way down. So on the way down, this will be positive and that'll be negative. And so I can define the terminal speed using that. So I get terminal speed is the square root of mg over b. Or you can simply think of this as a definition and don't worry about giving it any physical meaning. So I'm just defining a speed, which is lambda g. The true meaning of that is if you let an object fall for a very long time, it attains the speed. So on the way down is when it makes more sense than on the way up. On the way up, you see, it doesn't matter. You can throw a ball even close to the speed of light. It'll eventually, maybe after several months, stop due to the action of air resistance and gravity, and then come back. On the way down, it doesn't speed up beyond a certain point. Most objects don't speed up beyond 200 miles an hour. So if you jump out of a plane without a parachute, 200 miles an hour, you don't go faster than that. That's very little consolation for someone who is engaged in this exercise. But anyway, that's the terminal speed, and writing it in terms of R lambda, I get lambda times g. Observe it makes sense because g is meters per second squared, lambda is meters. So that's going to be the square root of meters squared per second squared, which is indeed some kind of velocity. So I'll put this cautionary note here. The speed may not be actually achieved. All right. So once we have defined this quantity, though, we can use it. Nothing stops us from using a quantity we have defined. So I'm going to rewrite y double dot as vy dot, and that is equal to negative. I'll take outside. I'll take a negative g outside. Now b over m is 1 over lambda, don't forget, because b over m is 1 over lambda. So I'm going to write that as 1 plus vy squared over g lambda. But lambda g is vt squared. So I actually have negative g times 1 plus vy over vt squared. That looks really cute. I'll do one more simplification. I'll take a vt squared outside. So I get negative g over vt squared times vt squared plus vy squared. I want to do the first part of the problem. And the first part of the problem does not involve time. So I want to get rid of time. An old trick of Newton can be used. Newton came up with all the tricks of calculus because the man happened to invent calculus too. So you can see that I'm a Newton man, not a Leibniz man. So dvy by dt equals dvy by dy times dy by dt. Later on, this came to be called the chain rule. So dy by dt is precisely vy. So this is vy dvy over dy. So I've written the left-hand side as that. And all that is equal to negative g over vt squared times vt squared plus vy squared. Okay, now this is a separable differential equation and can be solved. Vy and dvy are together. So I like to bring that down here so that all the terms involving vy are together, and then I'll take the dy over there. So separation is achieved in this manner. So I get vy times dvy divided by vt squared plus vy squared is equal to negative g upon vt squared dy. Now I integrate both sides. I'm going to put the limits this time on the integral itself. I start out with v naught, and when it reaches the highest point, the definition of the highest point is that the object is not moving. The ball is not moving. The height, meanwhile, has gone from 0 to the full height h. So that is our integral that we need to solve. The right-hand side is trivial. The left-hand side requires some substitution. The tangent substitution, well, actually, you know what? The natural log substitution is appropriate because the derivative of the denominator is in the numerator. So what we can do is let vt squared plus vy squared is equal to u. Then, if I differentiate both sides, vt is a constant. So that gives me 2vy dy is equal to du. What I will do is not mess with the limits. I'll do the integral and then switch back to the original variables. That way I don't have to worry about the limits. This is something I do often because I'm not motivated enough to change the limits in most problems. So taking the philosophy of doing the integral and then switching back to the original variables, I have the following next step. So I go from the integral. There's a 2 here that I need, which I don't have here. So it's going to be 1/2. And then I get a 2 vy dvy. That's a dvy here. dv sub y. Hope that's sufficiently clear. So in the numerator, I have 2vy dvy. In the denominator, I have vt squared plus vy y squared from v naught to 0. And that is 1/2 integral of v naught to 0 du over u. Well, that's just the natural log of u. And u is this. So it's a natural log of vt squared plus vy squared. And the limits are v naught to 0. Now I'll impose the limits. The upper limit is 0, so I get 1/2 natural log of vt squared plus 0 squared, which I won't write, minus natural log of vt squared plus v naught squared. Now all that is the left-hand side. Meanwhile, the right-hand side, so all this is equal to negative g over vt squared times h. So what I can do is I can take the negative sign over here and switch the order of these two terms. So I get 1/2 natural log of Vt squared minus V naught squared, plus V naught squared, minus natural log of Vt squared is equal to positive G over Vt squared times H. Now I can use the old trick. Now, combinations like this make me uncomfortable because natural log of meters squared per second squared makes no sense. But I can use the trick that the difference in logarithms is the ratio of logarithms. So I'm going to get 1/2 natural log of Vt squared plus V naught squared over Vt squared. And that is equal to GH upon Vt squared. One more step, I can divide both Vt squared into the numerator, and I get 1/2 natural log of 1 plus V naught over Vt, the whole thing squared, is equal to GH over Vt squared. So that's what we get on the way up. It's worth boxing. What is it? Well, you can think of it as an expression for the height reached. It's a pretty decent object to determine in a problem like this. You can actually predict how high the ball will reach. And you can do an experiment. You can ask your friend to measure how high it reaches. Your friend is somewhere on the 10th floor of a building, and you throw a ball and you measure the speed of the ball using some cell phone camera, for example. Ask your friend how high it goes, and you can see if it's the same as predicted by this formula. So there are many ways to verify this formula, and you can do experiments to verify if the ball is in fact going with this law. Now, let's talk about the phase of coming down, also known as the descent. As I mentioned, the equations will be different. So the only difference, though, is that the gravity term will be plus, because on the way down, gravity is helping the ball. So I'm going to get my double dot is equal to plus mg. Air resistance is still fighting the ball. Divide both sides by m, our famous trick. So I get y double dot equals g minus 1 over lambda y dot squared, and then take g outside to get the terminal velocity. This, by the way, is vy dot. So that's g times 1 minus vy squared over v terminal squared, just as we did in this first problem. That combination g lambda becomes vt squared. And then the other step we did was to take the vt squared in the denominator outside. So that gives me vt squared minus vy squared. You observe that there is nothing wrong with this because vy has always got to be less than the terminal speed. The terminal speed is never exceeded on the way down. And so the acceleration can at most be 0. When the acceleration is 0, that's when the terminal velocity is achieved. So we'll interpret the terminal speed at this point. Whether that happens or not in our problem, we don't know. If the height is not much, then the terminal speed is never achieved. But anyway, that's just the interpretation of the terminal speed. I told you it's on the way down that the concept of terminal speed even makes sense. Now, let's try to solve this equation. The solution is not going to be that simple. We can still separate the variables. So I'll play the same game. I'll write vy dot as vy dvy over dy. Well, all that is equal to g over vt squared times vt squared minus vy squared. Separate the variables, so I get vy dvy divided by vt squared minus vy squared is equal to g dy over vt squared, and now integrate. On the way down, the coordinate system has changed. Top is now 0, bottom is now h. So don't forget that. So the integral, the limits here are still going to be from 0 to h. So this integral actually is not as complicated as I thought. It's the time integrals that are complicated. This is again natural log, except they get a minus sign when you do the natural log. So rather than carry through, I'll just write the final answer. It's the exact same procedure there, except with the minus sign now. Minus sign, natural log of vt squared minus vy squared between the limits of 0 and v final. And that's going to be right-hand side is a trivial integral, gh over vt squared. Let's work this out. The upper limit will give me a contribution. The lower limit will give me a contribution. I'll get a difference, and a difference is the ratio of the logs. So I'll do all that in one step. I don't really have to be afraid about putting the absolute value bars, because like I said, VF is always less than the terminal speed, if not equal to it. So I'm almost here. What I can do is I can take the negative sign and cause it to flip it. I can take this negative sign and make it flip, okay? So I'll get positive half natural log of, first of all, I'll first divide by vt squared. So I get 1 minus vf over vt, the whole thing squared. And then I'll use the negative sign to flip the whole thing. So we have two equations that determine the height. One equation involving v naught, the other equation involving vf. Well, the right-hand side is the same. But if the right-hand side is the same, the left-hand side must be the same. So we'll equate 1 and 2. Hopefully, when we equate 1 and 2, we'll find out the relationship between v naught and vf, which is really what the first part of the problem is about. It is to show that vf is less than v naught. So let's proceed to equate them. One halves cancel out, so I get natural log of 1 plus v naught over vt squared is equal to natural log of 1 over 1 minus vf over vt squared. Now what I'll do is I'll strip the natural logs from both sides, also known as taking the exponential for you mathematical savvy folks. So 1 plus v naught over vt squared is equal to 1 over 1 minus vf over vt squared. Well, at this point, I'll clear all the denominators to make things look more manageable. So vt squared plus v naught squared divided by vt squared is equal to 1 over vt squared minus vf squared divided by VT squared, so that'll go upstairs like that. Now, what I'll do is simplify. One way to simplify is to cross multiply, I guess. So what I'll do is this. I'll take this, I'll bring this term to this side and take that term to that side, and then take this term to this side. Okay, so let me do that. VT squared minus VF squared is equal to VT to the power 4, because that's VT squared times VT squared, divided by this stuff which has gone down, VT squared plus V naught squared. So I can solve now for VF squared. That's my aim. So if I take the VF squared to the right, I can bring all this to the left, and then I can switch what I mean with left and right. So I'm going to have that. You can do this any way you want. It's just how it's coming to me today. And then this is VF squared is VT squared times VT squared, which is VT to the power 4. And then I have V naught squared VT squared minus VT to the power 4. You can see a cancellation happening there. VT squared plus V naught squared. So that's going to be V naught squared VT squared over VT squared plus V naught squared. Excellent. So I have VF over V naught. So what I'm going to do is divide both sides by V naught squared. So that gives me, this is equal to VT squared over VT squared plus V naught squared. Now, anybody can agree that this is going to be less than or equal to 1, because the numerator is always going to be less than or equal to the denominator. So this tells us that VF must be less than or equal to V naught. We have proved the first part of this video. So we'll write our grand conclusion. Thus, ball returns with slower speed. The second part of the video is to show that it also takes a longer time to come back than it did to go up. So that's going to be the second part. So we'll again split up the calculation into ascent and descent. So we'll go back to the original differential equations that we had. For ascent, we had this, Vy dot equals negative G over VT squared plus Vy squared. Let's go back to that equation. Now Vy, this time we're interested in time. So let's use the traditional interpretation of Vy dot. It's just dVy by dt. So now we'll again separate variables with the view of trying to find the time. So separating the variables gives me the integral of dVy. I'll bring everything with Vy downstairs. That's Vt squared plus Vy squared is equal to negative G over Vt squared. I'll take outside the integral sign since it is constant. That's the integral of dt. The limits are in the ascent phase, it starts with V naught, ends at 0. 0 time, the time taken to go up is T1, according to my picture here. T1 to go up, T2 to come down. This can be solved. This integral is rather straightforward. It's just a tangent substitution. So I start with Vy equals Vt tan theta. Then if I take the derivative differentials on both sides, I get dVy equals Vt secant squared theta d theta. Once again, I won't bother with the limits. I'll do the integral and then go back to the original variables and then put the limits. So I end up getting the integral from V naught to 0, Vt times secant squared theta d theta divided by, over downstairs, I have Vt squared plus Vt squared tan squared theta. And this one is just negative g over Vt squared times T1. So that part's pretty simple. One of the Vt's cancels out. So I get 1 over Vt here. The integral from V naught to 0, secant squared theta d theta over 1 plus tan squared theta. And that's equal to negative g over V terminal squared times T1. Well, that's the entire rationale behind the tangent substitution. Secant squared is precisely 1 plus tan squared, so I lose the integrand. And now I just have the integral of d theta. Well, that's the simplest integral in the world. The integral of d theta is just theta. However, theta is arctangent of Vy over Vt. So I'm going to write that result directly. So arctangent Vy over Vt times 1 over Vt, don't forget, between the limits of V naught and 0 must be equal to negative g over Vt squared times T1. Now, tan inverse of 0 is just 0. So I get 1 over Vt times 0 minus the lower limit gives me tan inverse V naught over Vt. And that's equal to negative g over Vt squared times T1. The negative signs you observe cancel out. One factor of Vt also cancels out. And so I can solve for time T1. The time T1 is what I'm interested in finding. So if I solve for time T1, the Vt comes up there, g goes downstairs, times tan inverse of V naught over Vt. Let's save that, because we'll soon need to compare T1 with T2. Okay, now that's the ascent phase. Let's look at the descent phase. In the descent phase, we'll be able to find an expression for the time T2. The differential equation in the descent phase differs from the ascent phase in only having that minus sign in between. So I'm going to just write that. So Vy dot is simply going to be g over Vt squared minus Vy squared, and that is dVy over dt. Maybe I should show you where I had that. It's right here. except I'm not messing with the left-hand side. The left-hand side is written as just Vy dot. The right-hand side is that. Okay, so that's that. And now we have to integrate this, again, by separating the variables. In the descent, the limits are 0 and Vf because it starts at 0 and ends at Vf. dVy divided by Vt squared minus Vy squared. And that's all equal to G over Vt squared. Once again, it's a constant, so don't worry about that. And the integral of just dt, t2 on the way down, okay? So we have to solve this. This is probably where you're in slightly new territory, because I believe hyperbolic substitutions were not something emphasized in the undergraduate curriculum. So this is a good chance for you to review some hyperbolic substitutions. So the substitution we're going to use is Vy equals V terminal tan hyperbolic chi. Now, just to give you a quick, lightning quick introduction, the sine hyperbolic is defined as e to the chi minus e to the minus chi divided by 2. Cosh hyperbolic is e to the chi plus e to the minus chi divided by 2. In fact, you can think of these as simpler versions than trigonometric functions, because trigonometric functions came by letting chi equal to I times theta. So the Euler formula for complex numbers is required to get sine and cosine from these formulas, whereas these formulas are more primitive. As a matter of fact, the hyperbolic functions came a full 9 years before trigonometric functions were introduced by John Wallis. So the evolution of the subject is such that these came first. Tan hyperbolic is just sine hyperbolic over cosh hyperbolic. So you see that there's a lot of similarity between hyperbolic and trigonometric functions. Now, because of the way these formulas work, you can actually get an analog for any trigonometric formula you know. For example, one famous trigonometric formula is sine squared theta plus cosine squared theta equals 1. Ask anyone, they'll tell you that. If you convert this to hyperbolic language, what happens? Again, because of the relationship between hyperbolic and trigonometric using the Euler's formula, what happens is that the sine squared gets replaced by sinh squared chi, cos remains cosh, equals 1. This leads us to what's called the Osborne's rule. Osborne's rule says that in any formula involving trigonometric functions, wherever you see the formula for sine squared, replace it with negative sinh squared. And that's true for even implicit presence of sinh squared. So replace sine squared by sinh squared. By implicit presence, I mean equations like this. I'll come back to this soon. So what if you had an equation of the form, you all know that secant squared theta equals 1 plus tan squared theta. How do you Osborne it? Well, it's very simple. Secant becomes sec. Sec is 1 over cosh. Nothing happens to cosh. So this is just sec squared chi equals 1. Tan hyperbolic is sinh over cosh. When I square tan hyperbolic, I get sinh squared. Osborne's rule immediately kicks in. Replace sine squared by negative sinh squared is what I meant. So Osborne's rule kicks in, and because tan hyperbolic squared has got sine hyperbolic squared, you have to replace sine squared. Because tan squared has got sine squared, you have to replace it with negative sinh squared. And then I have negative sinh squared over cosh squared, which is again negative tan hyperbolic squared. Now you see why tan hyperbolic is a very good substitution for this problem. Because you have 1 minus something squared, and that's going to give me sec. Differentiation works in pretty much the same fashion for trigonometry, but it's wise to do it case by case. I'll leave you to verify that when you take the differentials on both sides, this gives me Vt sec squared chi d chi. There is no Osborne's rule for derivatives and integrals. So derivatives and integrals should be done on a case-by-case basis. All right, that's my short segment on Osborne's rule, because I believe hyperbolic substitution and hyperbolic functions are one of those many things that have left the undergraduate curriculum. So now let us go back to the integral at hand. The integral here is 0 to Vf. dvy is Vt sec squared chi d chi divided by denominator, which is Vt squared, 1 minus tan hyperbolic squared chi. And then I just showed you here that they're the same thing, so we can cancel them out. Well, all that is equal to, the right-hand side is integrated trivially, so that's gt2 over Vt squared. So that gives me one of the factors of Vt cancels out, and I get 1 over Vt times the integral of d chi, which is chi. But chi is just inverse tan hyperbolic of Vy over Vt between the limits of 0 and Vf. One of the Vt factors cancels out. I can take the Vt over there, G down here, and so I can get T2. And then I evaluate the limits. The upper limit contributes, the lower limit doesn't contribute, because tan hyperbolic of 0, because of sine hyperbolic of 0 is 0. So tan hyperbolic of 0 is 0, and so the inverse tangent of 0 is also 0. So this gives me Vt over G tan hyperbolic inverse Vf over Vt. Yet another box-worthy expression. So now we have found both the times, the time for going up and the time for coming down. The last part, and this is what I consider the fun part, is to show that this is bigger than that. How on earth do you do that? The cheap way is to put them both on the computer and see what graphs they produce, and then you can convince yourself by putting numbers for Vt and Vf that is true. But that's the cheap way. We don't want to be cheap. So let's try to do this analytically. So the ratio, how do we do the ratio? T2 over T1 is the Vt over G cancels. So it's just tan hyperbolic inverse Vf over Vt divided by tan inverse V0 over Vt. Now, earlier I showed you something. When we did the first part of the problem, we have this very important result. So let's go back to that result. But Vf over Vt well, what I'll do here is this. Let me first write this. Vf over V0 squared equals Vt squared over Vt squared plus V0 squared. What I'm going to do is I'm going to pull the Vt squared down and take the V0 squared up. Okay, so I'll do that switcheroo. And then I have V0 squared over Vt squared plus V0 squared. So what I'm going to do is call, so let me just do this one more step. Vf over Vt is going to be equal to the square root of all that stuff. Now I'm going to divide by Vt. Vt squared. So I'll get 1 plus V naught by Vt squared. And I'm going to call the symbol eta to be V naught over Vt. This makes analytical work much easier. So I end up getting Vf over V terminal is equal to the square root of eta squared over 1 plus eta squared. Well, that's just eta over the square root of 1 plus eta squared. So that expression there looks really cute now. T2 over T1 equals tan hyperbolic inverse eta over the square root of 1 plus eta squared divided by tan inverse of V naught by Vt, which is simply eta. So it boils down to comparing these two. Now, just suppose that, let's just suppose we don't know what tan hyperbolic inverse is. So we have to figure out a way of thinking about that. So let me move to a separate inverse hyperbolic geometry zone. So this is new stuff for some of you, and that's good. So what I'll do is this. In order to find out what tan hyperbolic inverse something is, I'll just say tan hyperbolic inverse chi equals u. This chi is not related to anything before, just random stuff. So this tells me immediately that another way to think about that is chi equals tan hyperbolic u. Well, tan hyperbolic u is just sinh u over cos u. Now, by Osborn's rule, that is sinh u over the square root. Now, normally I would say cos equals 1 minus sine squared. So in hyperbolic speak, it becomes 1 plus sinh squared. So that is that. And so so this is really interesting. Chi is equal to all of that. Therefore, I conclude that sine hyperbolic of u must be equal to eta. So that way I have eta over square root of 1 plus eta squared right there. Okay, so this whole thing, this is a rough sheet. It is to show you that when you have eta over square root of 1 plus eta squared, what you actually have is inverse sine eta over tan inverse eta. So that's a much nicer looking thing. I'll bring this rough sheet back at some later point. Okay, this can be thought of as a ratio of two functions, f of eta and g of eta, where f of eta is the numerator and g of eta is the denominator. Now I'm going to quote a little result from calculus, which you probably all know. And the calculus result is this. Ultimately, I want to prove that T2 over T1 is bigger than 1. In other words, I want to prove that f of eta is bigger than g of eta. So this calculus result can be used. If f of eta and g of eta are both positive functions in their domain, then f of eta is bigger than or equal to g of eta if and only if the derivatives are greater. So this is the monotonically increasing functions have monotonically increasing derivatives. So that's a comparison. So the other thing we observe is that, so that's a theorem. Now our observation is that f of 0 which is sine inverse of 0, is 0, because sine of sine function at 0 is e to the 0 minus e to the minus 0 over 2, which is 0. So f of 0 is 0, and g of 0 is 0, because tan inverse of 0 also is 0. So this allows us to conclude something slightly more strong. We're going to end up showing that f of eta is bigger than or equal to g of eta for all eta bigger than or equal to 0. Here I have for all eta is bigger than 0. So the bigger than or equal to sign comes by fixing the ground level. Okay, so now we have our theorem lined up. All we have to do is find the derivatives. So let's find the derivatives. What is f prime of eta? That's going to be d by d eta of sine inverse eta. Now, since you don't know hyperbolic functions, I'm not going to assume that you'll be able to immediately see the answer. So I'll go back to my rough sheet and work it out for you. What is d by d eta of sine inverse eta? So think about how you did this in trigonometry. So the first thing you do is let sine inverse eta be something else. Let's call it v. That tells me that eta is the same as sine of v. So that is basically what inverse means. Now I differentiate eta with respect to v. d eta by dv is the derivative of sine, and that's just cosh. If you have any difficulty seeing that, all you have to do is take the derivative of sine, and then you see e to the chi is just e to the chi, and negative e to the minus chi becomes positive e to the minus chi. So the derivative of sine is indeed cosh. But cosh, thanks to Osborne's rule, is the square root of 1 plus sine squared v. And sine v is eta. So that's going to be the square root of 1 plus eta squared. Therefore, dv by d eta by Euler's theorem is just 1 over the square root of 1 plus eta squared. But what is dv by d eta? V is sine inverse of eta. So dv by d eta is precisely d by d eta of sine inverse eta. In this manner, we have solved the derivative of an inverse sine. Now, while I'm at it, let me also do the derivative of g. G prime eta is d by d eta of tan inverse eta. You probably remember this result because tangent is your friend and inverse tangent is your friend. But what I want to show you is you don't really have to remember even that. Okay, all you have to do is you have to do the same kind of trick again. So let tan inverse eta, I've already used v, so I'll use w. So that tells me that eta is tan w, and now I'll do d eta by dw. The derivative of tan theta is secant squared theta, but secant squared theta is secant squared w. Secant squared w is 1 plus tan squared w, and tan w is eta. So that's going to be 1 plus eta squared. What we actually need is the opposite. So again, by Euler's theorem, d omega by w by d eta is 1 over 1 plus eta squared. But w is just tan inverse eta. So that's just d by d eta of tan inverse eta. So we have found both the derivatives just like that. I never remember anything. It's always better to do the honest work than to remember all kinds of things in a slipshod fashion. So this is scratch work I'm copying down. So the derivative is going to be 1 over root 1 plus eta squared, and then g prime eta, which is the derivative with respect to eta of tan inverse eta, is 1 over 1 plus eta squared. Now we are done with this sheet. All we have to now do is to establish that the derivatives are monotonically are increasing in that fashion. So that's what we have to show. So let's establish that. To show that f prime eta is bigger than or equal to g prime eta. What does it boil down to? It boils down to showing that 1 over root 1 plus eta squared is bigger than or equal to 1 over 1 plus eta squared. Now, if you're able to see this, good. You're a gifted person. I'm not, so I have to do some more. I'll take 1 plus eta squared over there and square root on that side. So I get 1 plus eta squared is bigger than or equal to root 1 plus eta squared. Well, I'm kind of dumb. I don't even I agree with that. So I don't immediately see that's obvious. So I'm going to do one more step, which is squaring both sides. At some point, I'll see the light. So 1 plus eta squared squared is bigger than or equal to 1 plus eta squared. Okay, now that definitely looks bigger on the left. Let's do some more steps. This is going to be completing the square. I get 1 plus 2 eta squared plus eta to the 4 is bigger than or equal to 1 plus eta squared. Okay, now even I agree. It's looking better and better. So that tells me that eta to the 4 plus, bring the eta squared over there, eta squared is bigger than or equal to 0. Now, that is obviously true for all eta bigger than or equal to 0. Nobody can argue with that. It's a sum of the squares of two terms, and that has to be bigger than or equal to 0, the equality obtaining only if eta is 0. So we have proved that f prime is bigger than g prime, and according to the theorem, we have shown that f is bigger than g. So we have shown that T2 over, therefore T2 over T1 is bigger than 1. And so the time for descent is greater than the time for ascent. Verify this next time you throw a ball up in the air. Actually the time it takes to go up and the time it takes to come down. You'll find that the time it takes to come down is always going to be a little bit more.